Okay, so I'm just going to spend the next, pretty much the rest of the lecture here going over the first quiz. Rather than cover things directly out of the text, I thought I would just kind of guide you through this. I'm not going to give you the answers, but the first question comes from the JAW book. That's where this is coming from. So in the foreword, the author, and that's JAW, mentions the U.S. Federal Wind Energy Program. The question is whether it's part of the U.S. Department of Energy or not. So the U.S. Department of Energy does have different divisions. For example, last fall I was there in D.C. and met with some of the fossil fuel policy directors. So is this separate or part of the U.S. DOE? What does it do? And you're more than welcome also to go out and look online to discuss that. And then see if you can find the name of the director as well. Don't kill yourself. If you can't find it, just say, hey, it doesn't exist anymore, but I did my research, or it was disbanded, but it's just encouraging you to go out and research what resources are already out there for wind. VAWT, that's a vertical axis wind turbine. There's one sitting in the back of the classroom right there. The vertical axis means that the wind turbine itself is spinning about a vertical axis. If next time you're over there on main campus going by the rec center, Brian Kearns just had a vertical axis wind turbine installed. There's an LED lamp. There's a little bit of solar. He and I discussed the placement and decided that's kind of a good high visibility. The horizontal, or HAWT, those are the three-bladed type that you typically see. So your axis is either going to spin vertically like so or horizontally like so. And just find the name of the inventor of the vertical axis. And this is how I'd like you to answer this. This is also from the JAW text as well, not from Pigott. So according to JAW, who took the numbers and what percentage comes from wind? And just
two different numbers there, though.
Find the one that makes the most sense, and if you can substantiate your answer, you'll get credit for it. Okay. Figure 1.2 of Pigott. What names the author give to the location where the blades intersect? The posted PDF will have the same information. I was just going from the hard copy. So it's just a matter of finding that information in Pigott. Okay. Tip speed ratio, that's going to be something that you'll find in in JAW as well. And here's the way to think about it. So if you've got your turbine, I'm just going to draw a simple horizontal axis. You've got the wind coming in at some velocity. I'm just going to call this V naught. The tip speed, and I'll just call this V sub t for the velocity of the tip. There's just going to be some ratio between those two things. The way to calculate this tip speed is like so. So if I've got my rotor spinning, and I'm going to use omega. Omega is going to be measured either in RPMs or radians per second. And so let's figure out exactly what that is. So it's typically easier to think about something in terms of RPMs. If we walked out to the wind turbine behind us right now, we might see that thing spinning. I've seen it spin as fast as, gosh, maybe 1,000 RPMs, maybe a little faster. So let's just convert 1,000 RPMs into radians per second, and that's going to allow us to get the velocity of the tip. So let's just do that first off. So if I've got 1,000 rotations per minute, and I want to convert that to radians per second. So very simple just to convert minutes to seconds. So 1 minute is 60 seconds, and one rotation, so just taking, let's just call this tip blade 1 going all the way around, coming back to its original location, that's just 2 pi radians. So one circle is 2 pi radians. So 1,000 RPMs, we'll just run that through the calculator. 1,000 times 2 times pi divided by 60 equals 104. So it's about a 10-to-1 ratio. You can see because I've got 6, 2 pi in the numerator, I've got 60 in the denominator. That just comes out to be 104 radians per second. So 104 hertz. The units on hertz, so the units on hertz just equals 1 over seconds. You'll notice right here, we don't put any units on radians. They're not in degrees. And the whole beauty of using a radian, so if I've got a circle and I've got a radius of r, one radian is just basically taking that radius and wrapping it around the circle. As it turns out, that angle right there is 1 radian. And if I keep wrapping, eventually I'll come all the way around and I'll come up to 2 pi radians. As it turns out, that equals 360 degrees. So you probably remember that from trig class. Okay, so how does that convert from getting from radians per second or hertz up to the velocity? Well, the equation for getting tip speed, so the velocity at the tip equals, and I'm just going to let the radius of this circle, of this turbine, be big R, uppercase R. The velocity of the tip just equals the radius times the angular velocity in radians per second. Because the radius has dimensions of length, and the angular velocity has dimensions of 1 over time, as I just demonstrated here. So so hertz are measured in 1 over seconds, inverse seconds, and seconds have a dimension of time. So when I multiply radius times angular velocity, I get meters per second. So obviously the dimensions of tip velocity equal length per time, and it works out. So if somebody gives you something in RPMs and you want to find the tip speed, you're going to first have to convert that to radians per second so that the units work out. Okay, and that way you can get it into meters per second or feet per second, what have you. Okay, so that's how to think about tip speed. All right.
So what's the tip speed ratio?
I'll let you figure that out. It's in the book. It's just you just go and find it. I'm just helping you define what the tip speed is. I'm not going to answer answer the problem for you. So that's just, look it up, you'll find it, then you're done. But this is some technical detail that might be difficult to deduce directly from the book. But that's exactly how you find this out. Okay. All right, this, I think this problem might give you a little bit of a challenge, but if you think back to Energy 101, this is exactly the type of problem that you read in that very first summary on week 1 of 101. So this is just a more technical review of that. And so what I want to ask is, what's the energy of a cubic meter of air moving at 10 miles per hour? And here's the density. So this is just an energy equation. I'm not going to solve this exact problem, but I'll solve something similar. Okay. There's a lot of different ways to think about this, but here's your wind turbine. Here is your cubic meter of air. And the cubic meter of air could take any shape you want. It could be a cylinder, it could be a cube, it could be what have you. It doesn't really matter. I'm just going to draw it as sort of a flattened cylinder. And it is moving at some velocity. And I'm just going to say that velocity equals 1 mile per hour. And here it comes. It's going to make that blade spin. Well, maybe not. If it's a 1 mile per hour wind, you might not get any action out of it. But nevertheless, that cubic meter of air does, in fact, contain energy. Now, what's the proper formula to use for that? So energy equals 1/2 mv squared. It's just the definition of kinetic energy. I've given you the velocity. You got to figure out the mass somehow. So what's the mass of the air? Well, we know that mass is equal to the volume times the density. So I'll just convert that right now. Energy equals 1/2 volume, and I'll use a capital V with little serifs on there. Volume times density. So the bigger the balloon I have and the more dense it is, the greater the mass. Times the velocity squared. Now, the trick here is that I've given you this problem in, I've given you this in miles per hour, and I want that in, I want this in joules. So I'm going to have to take the miles per hour, convert it to SI units so I can get to joules. Okay, so from there, E equals, and let's just take that 1 mile per hour and convert it to meters per second. Google is reading my mind already. So 1 mile per hour is 0.447 meters per second. 0.447 meters per second. Yeah. So here's my 1/2. My volume is 1 cubic meter. The density of air is given in the problem statement at 1.2041. 1.2041 kilograms per meter cubed. And then the velocity, we've got 0.447 meters per second squared. So first of all, I'm just going to go through here and cancel some units. So the meters cubed are going to cancel, and I'm going to be left with kilograms times meters squared per second squared. So the question is, anyone remember the definition of a joule? A joule is a watt second. Another definition of a joule, 1 joule equals, what's that?
It's like a Newton per second. No.
Let's see, no, a joule is also a Newton meter.
Yeah.
A joule is also a Newton meter. It's 1 Newton times 1 meter. So 1 joule actually equals 1 kilogram times 1 meter squared over second squared. And then let's see, what's the definition of a 1 Newton? 1 Newton just equals 1 kilogram meter per second squared. So it's the weight of, it's the equivalent of about 100 grams of mass. 100 grams of mass weighs about a Newton. Okay, so that is in fact the definition of 1 joule. 1 joule of energy is 1 kilogram meter squared per second squared. So that works out. Now, from there, it's just a matter of saying I've got 1.2041 times 0.447 squared over 2 equals, let's just take it to completion, 1.2041 times 0.447 times 0.447 divided by 2 equals 0.12. 0.12 joules. Not much energy. Tiny. And that's what you'd expect. It's moving very slowly, and so the answer works out. And now, but hopefully you can see, from this, if I've got a bigger volume, you're not going to do much about air density. It just kind of happens to be what it is. If you stuck this thing under water, density of water 1,000 times that of air, the water moving past is going to have a lot more energy density than the wind. Okay. You can also see why the velocity is so critical, because you get a lot more bang for your buck because it's parabolic. The power equation for wind turbines is actually velocity cubed. And we'll derive that later. Okay, so here we go. Betz law. We'll look up what the Betz limit is. This is another good problem. I'm not going to take you all the way through this, but I will give you the key equation for it. So there again is power. Betz limit. What's the minimum diameter that the turbine might have? So let's just go out and take a look. I know it's in the textbook, but it's just as easy to go up and look up what Betz law is.
59%.
Okay. I think it's something like 16/27. There's a specific, and I really do like the derivation. I really do like the derivation on Wikipedia. I mean, we will not go through all the calculus on it, but there it is. It's 16 divided by 27. I love the fact that it's a pure fraction. So equals 16 over 27 equals 59.3. Now, why is that? Why couldn't you just get 100% efficiency out of a wind turbine? What's the problem there? What's kind of the fundamental problem?
Back pressure on the backs of the airfoil. Moving off the back.
Yeah, maybe. It does have a lot to do with the backside of the foil. Let's just look at it this way. Here's your velocity. I'm just going to call it VU for velocity upstream. And I'm just taking a side view that the turbine is actually spinning about this axis. If I were to look just sideways at that axis, it would be spinning up, or from the other side, down. Now, if I were able, and what would happen? So we just did a problem where we've got the energy here equals 1/2 mv squared. If I'm going to get all of that energy out of that wind, what's the velocity over here?
The same. 0.
It'd be 0. I'd have to get it all somehow. Sorry, not happening. I mean, it's just like, well, it wouldn't necessarily be a vacuum, but it would mean that all of that velocity would have to just sort of go somewhere else. You know, it would have to be moving. The fact is, no matter where you draw sort of your system boundary, that air's got to go somewhere. You know, it's going over here, it's going over here, it's going over here. You're never going to be able to make that velocity be 0. If you could, yeah, you'd have a 100% efficient system. Or maybe like, hey, let's invent something where the air comes in, maybe it bounces off. Well, it's still going to have some energy coming off there. As it turns out, Bett's limit, this 16/27 comes out of the fact that the average velocity, so I'm just going to call this the downstream, right in here, like the velocity in the system, I'll just call this the velocity of the system, equals V up plus V down over 2. The velocity inside the system makes sense. It's just the average. It's fast upstream, it's slow downstream, somewhere in the middle is the mathematical middle. So that's kind of the theory behind Bett's limit. If you can beat it, let me know. Okay, but back to the problem. The equation we're going to look at, I'm just going to grab it out of the book here. And there are a couple different ways to derive this. Let's just go back out to Wikipedia here. Yeah. This is basically what we're looking at right here. There's your efficiency, there's your 16/27, and this equation right here is more or less the energy equation turned into a power equation. So there's that density again that we just saw in our energy equation, and now this velocity cubed, really all we've done here, so that S, it's area. It's got dimensions of length squared. This V still has the same dimensions it had before, length over time. So really all we did here, we took volume and turned into area, and we took one of those lengths, stuck it over there, turned it into velocity, stuck another time in the basement, and now we got velocity cubed. So let's just take that. So power equals efficiency times 1/2 density area V cubed. And let me just, for clarity, energy equals 1/2 m v squared, or energy equals 1/2 density times volume v squared. Now we know that energy equals power. That's not a rho, that's a power, times time. We also know that power equals energy divided by time. So if we just take this guy right here, and I'll just derive it for you really quickly. Power equals 1/2 mv squared over time equals 1/2. So mass is density times area times velocity squared over time. So again, we're calculating power. Really, all that's happened here is the, oh, sorry. Hang on, sorry. I'm going to typo. Where is it? Density times volume. There we go. I converted mass to density times volume. From there, it's just a matter of taking that volume, so 1/2 density area, which in this case the authors of the website have written as S, times length. So area times length. And what length am I talking about? Well, all the way back to this first problem, it's just the length of that chunk of air. So here's the area of it, and there's the length moving through space and time. So volume, area times length, velocity squared over time. Now I'm just going to group that length divided by time, and I end up with 1/2 rho S V cubed. Now, this would be the average power. As I just mentioned with Bett's law, the best we can do is this efficiency. So this entire, then from there, this would be the maximum total power that you could get from the system if you could capture 100%. So to get to the final answer, you throw the efficiency in front, eta 1/2 rho S. Remember that S is area V cubed, and you're done.
Aren't you solving for S in that equation now?
Yeah, in fact we are. Yeah, perfect point. Thanks for jumping to that. So what I've done in this problem, we're going to start out with power equals efficiency times 1/2 rho S V cubed. And you're exactly right. To solve this problem on quiz 1, what I'm asking you for is how big is the turbine? You're looking up at it, like, oh my gosh, thing's cranking away at 10 kilowatts, and you can't measure it. You're not going to climb up on the tower with a ruler. So this is an example of reverse engineering, more or less. Your S equals the power over the efficiency, which we just calculated, which is 16/27, times 1/2, times the density of air, which I believe is also given right there. Let's see, power over the velocity cubed. So I've given you the power, you know what the efficiency is, the 1/2 is given, you know the density, and you know the velocity. So it's just one equation, one unknown, plug and chug. Once you know S, I'll just write it this way, or A, the area, you then know that the area equals pi r squared, or r equals the square root of the area over pi, and then from there you can get the diameter. The diameter just equals twice the radius.
The
And you're done.
velocity there is in meters per second again, right?
Yeah, and just be sure that you're using constant. Don't mix your miles per hour and your meters per second. Will not work. So I've given this to you in miles per hour. In general, it's almost always easier to work in SI units. Just take your velocity, convert it to meters per second, and proceed. The kilowatts. This is not in horsepower. And this is not in slugs per cubic inch. So, there you go. Okay. So hopefully that helps you get through that problem. I know it will. Okay. In order to find the overall efficiency of a wind turbine, the efficiencies of each component, think about this a little bit. We can just, and what always helps is to draw a picture. So here's the turbine. You've got you're going from you're going from some kind of electrical signal that's doing this. It's all over the map. Typically, there's a rectifier in there. It's going to take that to a DC current. There's some total DC current. It's going to take it from AC into DC. From there, it's going to be converted into AC. All along this thing, you've got line losses. There's no such thing. Well, in a typical wind turbine, you've got electrical resistance. We don't have superconductors in this thing. So you've also got line losses before you get to your outlet. So here's your primary energy, and we've just been doing that problem all day long. What is the energy of the wind? From there, you're gonna have some kind of loss. We already talked about the Betz limit. So now you've got, and I'll just call this energy primary. From here, you're going to have energy. I'll just call this. What's a good name for that squiggle? I mean, it's going round and around. We'll just call it.
It's the same as the factory in that drawing. Where we're looking at 101? When you go from the coal in the ground to the factory, what the factory output is.
Yeah, I mean sometimes it's called secondary energy. We can just call it that. I mean, once it's sort of gone through the technology, it's all secondary, and obviously it's less. And then from here you're going to go. Let's just say energy DC, and then you're going to go energy AC. Each one of these is going to have some efficiency. In general, you might lose, if your lines are short, you might lose 1 to 2% through this. Every inverter, go stick your hand out an inverter, it's hot. So it's radiating, like that's its loss. Even the little electronics in the back of the room here, they get hot. They're radiating and losing electricity. So
Good one's 93%.
yeah, 93% is a pretty good estimate, because there's no such thing as a perfect conductor, at least in these type of technologies. So I'll leave it up to you to decide how you multiply, divide, add, subtract the efficiencies as you move through the system. So just think about what you did for this first step to get through the turbine, to get from your primary energy to secondary. And the answer should be revealed in terms of how you get to your final. Okay. All right, so again, this was JAW. The book's a little bit old, so just go with what you see in the book. And this is an essay question. I just want to see that you've thought about this problem. I go, JAW was written X years ago. The number is greater now. This number is always going up, et cetera, et cetera. Is it accurate? Tell me. Do some research on it. If it's not, tell me why.
I don't see that in JAW, because what I see in JAW is 10%.
Where do you see 10%?
United States. No.
Yeah.
Right here, page 9. Two paragraphs down, about the bottom.
Okay.
So,
Well-
US energy planners predicted that wind energy sources could supply 20% of the country's electricity needs by 2030, up from the current 10% electrical energy generation from wind turbine technology.
Strange. Okay, let me read that. Because the next paragraph says, although wind energy consumption in the U.S. represents less than 0.5%, so let me read what you just said. T. Boone Pickens. Okay. Energy experts predict that to meet total U.S. energy requirements, wind farms, so this would be total, I don't know if this is electrical energy or not, to meet total U.S. energy requirements, wind farms covering approximately 750 square miles, roughly equal to the size of Texas, California, Montana, and Florida combined, some of the largest states in the Union, would be needed. U.S. energy planners predict that wind energy sources could supply 20% of the country's electricity by 2030, up from the current 10% electrical. That is weird, isn't it?
But you have on page 3, 1.2, it's pretty much verbatim what it says there.
Yeah. Well, that's probably not the only typo in the book. Yeah, that is, wind energy consumption represents less than 0.5%. Now, there are some typos in the book, and you might point that out. All the more reason to go out there and do your own research.
I know it's higher than 0.15, but I also believe it's less than 10%.
Yeah, I think 10's too high and 1.5 is too low. That's, yeah, interesting. Okay, so, do a little research on what, I already told you a little bit about the horizontal versus vertical. One thing I do want to cover is the difference between a Darius and a Savonius wind turbine. So D versus S. A Darius wind turbine is lift-based. The Savonius is drag-based. So the principles of lift are such that, and again, these are both vertical axis wind turbines. The lift-based system, and it's working on Bernoulli's principle. If you've got a stream of air coming in like so, what ends up happening to the individual air particles, molecules, is that as it goes past, there's actually more distance between the particles on the top than there are between the particles on the bottom. This decrease in distance makes so the distance goes up, the density goes down, so the pressure goes down, and therefore the force well, the force goes down too. So you've got a vacuum force. So on the bottom, the distance between the particles is closer. Therefore, the pressure goes, or sorry, the density, therefore, is higher than the bottom. The pressure, and this is kind of easy to understand, the pressure, so capital P, or sorry, non-rho, little case p, but non-rho goes up. If you've got a positive pressure here, it pushes the it pushes the blade. I've just sort of drawn a cross section here. Every Darius blade is going to look something like an airplane wing, going around and around in a circle. The drag base, it's just a parachute. It's cupped like this. Wind comes in, stops it. You get high pressure in the middle. You've got low pressure on the back, and it pushes it around and around in a circle, just like an anemometer. That's the fundamental difference between the Darius and the Savonius. I had a team of students a few years ago that built a hybrid combination, Darius, Savonius, where they had combinations of both. Savonius is low gear. Think of low gear, and the Darius is more of a high gear. So low gear means high torque. So good startup characteristics. The Darius is low torque, sort of better high velocity characteristics. Is one better? Is one worse? Well, it's kind of a moot point. What's the best renewable technology? Depends where you are. But both of them are better in the vertical axis wind turbine is better for low elevation, low height, and variable direction. Versus the horizontal, they're all going to turn into the wind, but better we have consistent prevailing winds. Okay, so that's the difference between.
Which one is that one?
Oh, that's a.
It would be a Savonius.
Yeah, it would be a Savonius. I don't think.
Drag.
Yeah, I don't think there's any lift going on there. That'd be a good one to figure out, though.
It's definitely a drag base.
Yeah, I'm just wondering if you get any lift out of it at all. I just said the A word that answers that question. And this is just a matter of going out there and looking this up. This is a good problem. You'll go out. You might see. Well, I'll let you figure that one out. I'll just let you know though, the biggest turbine we own here at the university is 10 kilowatts. We've got a on the back. I think that's probably what, a 1 watt.
Yeah, probably.
We got a 1 watt,
Like that.
100 watt. We got a kilowatt back on the trailer, and then the Hellgate turbine is a 10 kilowatt. So, all right. Well, I hope that helps. Any other questions for wind and solar? You've got access to the materials. I do not have a. Well, actually, let me breeze through this a little bit. I haven't really caught up on the introductions. So Noah has introduced himself. 5th-year student, graduated, environmental engineering. Perfect. Oh, good. I'm glad he took Peter's course. All right. Well, Noah, we look forward to you too. It's an interesting pet you have there. Ferret, okay. Zach, good to have you back. Graduating in the spring, looking for further STEM degrees. Dalton, fifth year business student, oh, super, fantastic, okay. Consolidate, drive, learn more about the industry, perfect, perfect. Ooh, yeah, do ride that unicycle to class. There's a guy in town with a giant unicycle. There's Gary. Perfect, good, good. Good. Okay. Tanner was just here. I love that. Energy is the only subject that interests me. That's all I need to know. Good. And Francis, you'll check in here too when you get a chance. Okay, super. Lynn, I've already answered. Levy, I think David wants to get a job in the big wind industry, and I've got a couple of students who've done that. Serenity was just here. Shauna is working on wrapping up her degree. Lynn's working on her certificate. Matt, it would be great to hear from you a little bit more, maybe see you in class. I know you're kind of busy with job and family. So, okay, those are great introductions. I'm also realizing I did not, I didn't put an assignment 1 out there. So just for the record, don't worry about assignment 1. I will give you something to do. Tim just gave you an assignment to work on, so focus on that.
Makes up for it.
Yeah, there you go, makes up for it. Focus on that for now. That thing will. Well, just, I'll say, mea culpa on this. This semester was off to a little bit of a rough start, to say the least, so I'm letting you ease into it a little bit, so. Okay, at this point, I think we're all caught up.
Too many greenies.
Yeah, I know.
Too many greenies trying to make biodiesel while smoking local shrubs. This doesn't work.
These old iTunes U lectures, I will get rid of them, so don't worry about those. You'll see the brand new, fresh YouTube videos that I'm putting up. So, everybody, thanks a lot. You've got stuff to work on, and anything else before I let you go?
When does the quiz need to be completed by?
I'd like the quiz finished before we meet next week. So just knock it out before.
Open it up so I can do it again?
Yeah, I'll open it up right now so you can. I think I already
We're
did.
gonna go
But,
see if we can
We're
get
gonna
the
go-
hydrogen truck.
We're gonna go put a,
okay.
We're gonna go replace
Throttle
that part right
sensor.
now.
Oh, fantastic. Thanks.
hydrogen truck.
Knock it out, guys. I can't wait to see it. Thank you. Take some pictures.
Yeah, we're gonna, if it works, we'll be out here in the fall.
Take some
If it
pictures.
works, we're gonna be out here spinning some rodeo.
All right, I want to hear that. Squeal away. Yeah. Just don't roll it. All right.
That have broken first place?
It